Donna's interest is in understanding hidden threats to heritage materials so that conservation strategies can be developed. Donna works with both the Chatham Historic Dockyard, just up the road, and with Mary Rose Trust projects that are related to long-term preservation of historic ships. Welcome, Dr. Donna Arnold.
I should start by saying thank you very much for the opportunity to be here today. I'm going to change track a little bit and talk about work we have done rather than work we need to do, but I'll try and put it into context as we go through and how this then feeds in perhaps to the Sheerness projects and heritage in Sheerness and Sheppey more widely. So originally I trained as a chemist. I've done a lot of work in new materials chemistry, so oxides. With a view to sustainability, we've been interested in electronics materials that use less energy. If we can use less energy, then maybe our batteries don't need to be as strong. I teach forensic science, so I morphed a bit into forensic science, and we've been looking at assessment of materials and technologies for forensic analysis and for moving into forensic. Does something match? Does it not match? And again, from a viewpoint of sustainability, if I go into a room and there are 100 brown stains on the wall, currently I would swab all 100. If only one of those is blood, if I've got a device that can tell me, then maybe I only need to swab one, which goes into the sustainability. And then I've also been interested in using these same technologies, so the same analysis methods that we use in heritage, and looking for hidden threats. So what is threatening our heritage preservation, conservation, and keeping it there for us to be able to see it for the future. And then again, heritage is another sector where we have to be considerable of sustainability and climate change. So it's no good if we preserve something, but it's coming at cost of not meeting carbon neutral, for example. And we've also been involved in investigating unknown finds. So if something's dug up, we don't know, it looks old, could it be relevant? Can we link it to something? Can we link it to the historical record? But to do that, you need to kind of know what it is. So we've been involved in working with some local historians who have local finds, and we've been trying to work out what they are. So what we've been doing is we have to consider first the need of the heritage site. As scientists, we tend to be pretty good at finding a problem and just running at it for academic curiosity. And we have to remember that there's a need driven here. We can't just think of things that we might like to do just for fun. We need to do them for a need. We have to think about what we need to answer and how we go about that. So in a science context, I cannot get a building as beautiful as this or the Mary Rose into my laboratory. I was asked on a grant application why I needed a handheld instrument. My response to the reviewer was because the Mary Rose won't fit in the lab. So, you have to think about what we're going to do. We also have to think about, is the technique destructive? I can't take a beautiful Roman coin, stick it in an instrument that comes out with beautiful Roman coin powder. Right? That doesn't show anything. I have to think about fixed lab versus mobile lab. So this is the terminology they use in the sector, fixed lab and MoLab. Mobile means we can take it to site. Fixed means it's stuck in my laboratory, and whatever I want to has to take to it. I have to take it to it. What data do we want to collect, and what's the cost and accessibility of that? There's inevitably a cost involved in analysis, cost involved in everything these days. But we have to think about, with heritage, what is that cost and is it worth paying? And what can we get? Well, we can get identification. We can work towards preservation and conservation methods. We can look at age, which helps us then think about the historical record and link it to historical studies. We can think about, is it authentic? Some of the instruments we have are really good at telling you if it's diamond or not, for example. So, we can often tell if something's a forgery based on what it was used. So paintings is the obvious example. If it contains a certain pigment, then it was probably painted after a certain date, which can lead to whether or not it's authentic. And that can also help with determining provenance and starting to be able to feed that through to museums. So I had a quick schematic here about scientific conservation. So this is my crude ship. You can see here we've got a growth. The first thing we need to do is identify it. So in identifying it, is it something that's going to cause damage? Is it something that's fairly benign, so won't cause any trouble? In which case, we're probably better leaving it there and just accepting it's part and parcel of our package. But if we decide it's something that could be aggressive and could lead to damage of our artifact, then we can develop a treatment and then we can remove. And again, with treatments, we've got to think now about sustainability. We've got to think about the damage it might do. It's great if you have something that will remove the unidentified powder, the red powder we have here, but it's no good if it also damages the underlying heritage item. So you now have two things you've got to consider. It's not just a case of does it wash off, it's what happens if I do wash it off. And then hopefully we have removal. And this slide, I was just trying to show some of the equipment. We have everything from the little handheld metronome there, the little green thing. And for those of you who remember Sony Walkmans, it's about the size of a Sony Walkman. I say that to my student and I get a sea of blank space faces. It's a bit bigger than a mobile phone. Through to the top equipment, there's an X-ray diffractometer. That's in the lab. That has a footprint of about the size of this table. Then you can take it to central facilities. We're very lucky in the UK. We have the neutron and the synchrotron facilities based just outside Oxford. That's the synchrotron ring. It's 1 kilometre all the way around. So, you know, the scale of what we're taking. So everything from being able to take my instrument into site, onto site, do analysis in situ, through to I need to take something with me somewhere else. And actually, the Mary Rose has pretty much been through all of those things. So what are the problems that face in large-scale heritage? And I've mostly worked on ships, so my heritage ships, but that equally translates to buildings, to heritage infrastructure, heritage farming equipment, for example, or in manufacturing, industrial heritage, is how do we protect it? And from a ship point of view, we've got the consideration of whether or not we put it in a purpose-built museum, such as what the Mary Rose is in, but now we're controlling humidity and temperature. That comes not only at cost, but there's also green implications to that. We could put it into dry dock, but then we have a different environmental and ecosystem growing around our ship. We can put it in wet dock. So currently some of the vessels at Chatham are wet dock. So Cavalier is in wet dock, Ocelot is in dry dock. So we need to think long-term what's happening. And also changes to our environment mean that conservation strategies that were developed 30 years ago are not necessarily relevant anymore because our average temperatures have swung. So we don't freeze as often, we don't get heavy snowfall as much, but 30 years ago, we didn't see weeks of 35-degree heat. So, that changes the chemistry and the biology that's happening in our heritage artifacts, and we have to consider that when we're considering preservation. So what I wanted to do was, rather than show where we need to go in the future, hopefully I've indicated that a little bit, but what I wanted to just show you is some of the work we've been doing and give you a little bit of a highlight of how things have been going. So this is the Mary Rose. She was King Henry VIII's warship, and she sunk in 1545. She was raised from the Solent, so just off the coast of Portsmouth. 1982, 1983, somewhere around there, so the early 80s. She was sprayed and kept wet to stop her timbers from shrinking, and then she was coated with polyethylene glycol, which is common practice for timber ships, with the hope that then they wouldn't shrink anymore, so it fills the voids that the water has taken away. But we don't really know much about what happens to PEG as we leave it for decades and decades and decades. But that's not quite where we came in. We came in with the bricks. So when my collaborator, Dr. Ellie Schofield, come to me and said, we need to look at some bricks. I was like, there were bricks on the Mary Rose? Like, it's a timber ship. Why were there bricks? There were 3,000-ish bricks on the Mary Rose. They were used for ballast. and they were used to form the galley, so where they cooked for all the sailors that were on the ship. You can see here, this is just a picture of what they think it would have looked like. And these are some of the bricks that are in a controlled temperature environment. The reality is you can't put 3,000 bricks on display in a museum. So the rest are in storage. And what's happening is we're getting some kind of formation in the pores. Bricks are porous. We're getting some kind of formation of something in the bricks. As it grows, it breaks the bricks apart, and we're just left with a load of bits of brick. Now that's kind of useful as a heritage science, because now I've got bits of heritage brick I can take into the lab. So now I have bits small enough to put in an instrument without damaging them first. So what we've been doing is we've started to look at what these salts were. So if we can understand what they are, then we can understand how they behave chemically, and then we can understand why they're damaging the bricks. And until we've done that, we can't actually get to the treatment stage or the preservation stage. So this is some microscopy that we did, and you can see here, this is the salts that are growing on the surface of the bricks. This is what they look like when you put them under a microscope. So you can see they grow in quite great structures. So they grow in particular ways, and that's what's doing the damage. And we can see they contain calcium, iron, and sulfur. The sulfur, it picks up from the seabed when it was under the water. The calcium and the iron are coming from sea life and from the iron nails that were rusting alongside that ship as they were stored. So once we identified them, we needed to see a route. If you're developing a technique for preservation, we need to have a route to know how much of something was there. So if something is effective, we need to be able to see that it's disappearing. And that might not be as simple as I treated it, it went away completely. We might need to track its disappearance so we know how many washings to do, how long the treatment to do, how do we go from here. So what you can see here, I'm not going to get lost in all of this, they're just pretty graphs, but you can see that we've identified most of the peaks here, and we're seeing iron sulfides and calcium sulfates, which is the same problem that the timbers saw in the Mary Rose, but also in Vasa in Sweden, and as they've been developing the treatments. So unsurprisingly, the bricks are facing the same problems that the timbers did. So that's a good place to start. Oops, sorry. We also did quantitative analysis. This took some effort. So we took this to that big synchrotron, so the big ring. We collected some data, and we're able to say now how much of everything is there. So if we treat it, we'll be able to say, okay, we had 30% before, we now have 5%. Perhaps if we treat it again, we can get it all the way. Or is 5% of this corrosive stuff acceptable? So again, that sustainability angle. If I treat it multiple times, what benefit does that give me? And if you translated that to something like a building, clearly, you know, we may want to treat buildings. They do. There's literature out there that suggests that buildings on the coast suffer the same problems from the seawater blowing in, that everything, especially heritage buildings. So if you're going to treat a building, you cannot treat it the same way you would a single brick. So now it may be what's acceptable to prevent further damage and to keep it in a state that we can all enjoy. So effectively, this is what we're trying to do. We've been looking at ways to remove it. So on our broken pieces of brick, with the ultimate goal of moving to a whole brick that we mustn't damage. So at the moment, we still very much work over here because these are already damaged. They're considered an acceptable loss. We've also been working with the Yenkapi 12, which is in Turkey. And this ship is considerably older. It was from about 672 to 876. And it was carrying all these amorphous vessels that had things like coins in. And this was a series of, it's 12 because there were multiple shipwrecks on the same site that University of Istanbul recovered. And they got in touch with us, and it was the same question. We can see salt formation on these timbers. What are they? Guess what? They're the same ones we're seeing everywhere else. But now we have to consider, if I develop a preservation or conservation methodology for the Mary Rose bricks, which are housed in a warehouse in Portsmouth, versus something that's now being housed in a warehouse in Turkey or a museum in Turkey, what kind of different conditions do we have? What's the difference in conditions that we need to consider? And again, this is where we need to think about sustainability and climate change and how that affects different regions, and that conservation strategies may not be the same depending where you are. And at the moment, it kind of is. We all kind of go with the same data from the 90s. So I think science can play an important role. And it's really nice to speak at an event like this where, speaking to stakeholders, to community, to people interested in preserving the dockyards here. This is important. Science has been this hidden thing. People do it. Nobody tells you about it. It needs to be part of the narrative. And we need to include it as part of the stories that we tell about sites. They don't magically get restored. There's a lot of work behind the scenes, and all of that work should come out in the narrative of the heritage site and how we did it, why we did it. But also, we don't really think about the future too much. We preserve it for now. We get the funding, we get it restored, but we don't think about, certainly with some of these things, the Chatham ships, the buildings such as this, it's still being attacked by threats, right? So we need to think long term what our ultimate preservation strategies will continue to be. What treatments is this going to need in the future? What funding are we going to need in the future to maintain this and to keep this at the level that people can enjoy it? Like I said, salt is a problem. Unsurprisingly, it's the same problem we're seeing at Chatham, and we're working with them to look at some of that. We also have net zero agenda. Long term, we cannot put buildings, trains, industrial infrastructure, heritage infrastructure into our ships, into museums with controlled temperature and humidity. It burns natural gas and uses a considerable amount of energy to maintain. So we need to understand how we can actually preserve in a way that doesn't consume as much energy so that we can contribute. And I know that this is certainly something we are working with our partners on. And like I say, I think the science needs to be part of the community and part of the story and not hidden in the, we spoke to some scientists at the university. And like I say, speaking here is a great honor to be able to communicate that. So hopefully I haven't bored you too much with the science, and you've been able to see at least something on the slides. And thank you very much for listening.
Thank you very much, Donna.